Okay, hi everybody. If you can, turn on your video today when we're doing problems and doing things, and it's easier for me to get a response, like how you're doing and whether you need more help. You can raise your hand and say, I'm not ready yet, and stuff like that. If you can, turn on your video. As a teacher, we're not like radio broadcasters where we have an invisible audience. Teachers really like to be able to see faces and how you're doing, and if you're smiling or you're going crazy. If there's a reason to turn off your video, turn it off, like bandwidth, if you have other people using it, or there's something going on in the background and you don't necessarily want to show the class, which is fine, you can turn that off. But if you can, try to leave it on. I feel better, especially at the end of the day. You know, we've been working all morning on classes, so got to keep my energy up too. Okay. Hi. So a little feedback on your quiz last week. Almost everybody did well. The average out of 20 points was about 18. And if you got less than 12, then you're going to scramble a little harder this next unit, which is chapter 3, finishes what we're studying right now. And what? Oh, homeworks, if you have less than a 6 out of 10, you can always ask for an extension still, and I can do that for you personally. Labs, make sure those, you got to get those in. Those are huge. And we're going to do another one on Thursday, predicting trajectories. Okay? All right. So nice to see you all. Good afternoon. It's going to be a really nice afternoon, so let's get started. So you have 2 coins, and this is chapter 3. And if you have 2 coins, otherwise you're going to do a virtual demonstration with other people in your class. So I have two quarters right here, okay? And we're going to set 1 quarter on the edge of your desk or your table, right on the edge, so it's ready to fall off. And the other one, we're going to slide into it so at some speed, so that the one on the edge falls down, and the one that has some speed will go out into the room someplace and land on the floor. The question is, which one hits first? So who has coins? Wave your hands. Who has 2 coins? Who's actually going to try this? Nobody? Nobody has 2 coins? One person. 2 people. Okay. All right. See if you can, see if you can actually try this, and then once you've tried it, give me a wave. And oh, here's Evan down here. Is Noah Jensen here? He's not yet, right? Noah Jensen. Turkey, keeping me from having perfect attendance. Who's trying this? Wave your hand if you're trying this. Okay, good. Try it. Try to run 1 coin into the other so that one just drops off the edge of the table and the other goes flying across the room, and tell me which one hits first. Go ahead and try it, and then you can tell me. This has everything to do with today's lessons. I don't do this as a demo usually because I usually don't hit it, and I miss the coin I'm supposed to hit, and it takes me forever to get it to work. Okay? As soon as you've done it, give me a high sign and tell me what happened. Who's done it? I had 3 of you trying this. Okay. Kate, are you trying that over there? Okay. And Edith, who's tried this and can give me some results? Come on.
So are we trying to get both coins to fall off the table, but one of them just
Goes farther.
Okay.
And then we're trying to find out, do they hit at the same time or at different times? Anybody else get some results? This is the qualitative demo. We're going to calculate stuff in a minute. All right. Sophie went to go find her coins, rolling around on the floor. Did they hit at the same time? Who's got some results for me? Edith's still trying it. Connor, did you try this?
I just tried it and it seemed like they hit the ground at the same time.
Exactly. Thank you. I'm going to use your results for everybody. Okay. They hit at the same time, exactly the same time. I'm still waiting for one I think everybody's here. Is Noah Jensen here? Noah Jensen. Oh, okay. Probably come in later. All right, so let's do this. You ready? I'm going to switch to Elmo mode, and you're going to start taking notes like crazy. You ready? Let's go to Elmo. And today's let that zoom in. Here we go. Okay. And if you can't see it, you have to say something, because on my screen, it's just a little tiny square. So here we go. So today's the 5th, and this is chapter 3 stuff. And today's class 8. Amazing that we've been in classes this is our 5th week already. Okay. So let's draw a little picture. Here's your tabletop. You've got a little coin that's sitting on the edge. Okay. And another coin that's going to run into it at high speed, so that the coin on the table falls down, and the one that's going fast into it lands out in here someplace. Okay. Now, from what you heard from anybody that has tried this, they do hit at the same time. Absolutely do hit at the same time. So that's an observation. And then from physics, we're going to be able to explain that and calculate a few things. So they hit the ground or floor at the same time. And that's what today's lessons are about. Today's the beginning of chapter 3. So it's trajectories, starting trajectories and vectors. We'll get to all that today. All right. And they hit the ground at the same time. Now I'm going to mention where a story came from. Now, who in here has shot a gun that fired something out the front, a Nerf or a bullet or anything? Who's fired a gun that something came out the front? You have, right? Most of you have. So here's the story. Here's the question. If you went up to a hunter and they had a rifle, they're a deer hunter or something, and they fired that rocket horizontally, that bullet horizontally, and at the same time they pulled the trigger, their friend dropped the bullet let it drop down to the ground. And one bullet's going out at almost the speed of, more than the speed of sound. The other one's going to be dropping towards the ground. The question is, which one hits the ground first? From what you just saw, which one hits the ground first? They both hit at the same time. Probably if they haven't had physics, probably what would they say? Probably the guy shooting the gun would say, oh no, mine's going so fast and it's going so far that it would not hit the ground at the same time. That's what they would say. But physics-wise, we know that they would hit at the same time, neglecting air friction. All right, so here we go. So we're going to say there's 2 rules that you're going to learn today. 1, horizontal in the x-axis, horizontal motion does not, N-O-T, does not affect the vertical motion, which is up and down. Rule 1. Neglecting air friction, there's nothing that affects the horizontal motion. It's just uniform horizontal motion all the time until it hits something, okay? So that means they are independent. So X and Y motions are independent of each other. Independent, not dependent, but independent. They're independent motions, okay? And they have to be considered separately, okay? All right, so let's see how we can develop stuff like that. All right, we're going to do a drawing now, and I'm going to back this off just a little bit so you can see what I'm trying to do. I want you to draw 2 16-centimeter lines on your paper, one near the left and one near the center. So, and you're going to label every centimeter on it. So I've got a ruler, and that's going to be the top of a building. Okay, 16 centimeters. We're going to scale this later, and then you're going to mark every centimeter on it. 1, 2, 3. I would send this worksheet to you, but some of the kids don't have access to a printer. And I think you actually learn more by doing something like this than just seeing it or doing it quickly. So we're going to take our time. And if you have any questions, just speak up because I'm not looking at you right now. 13, 14, 15, 16, okay? And this is the bottom down here. And we're going to do another one in the middle of the page that's 16 centimeters. This is for a future step. Okay, let's go over here. 16 centimeters. We're going to label that 16 times. Okay, so 1, 2, 3, 6, 7, 8, 9, 10, 10, 11, 12, 13, 14, 15, 16. And those are centimeters, okay? And the same things, and there's a 0 on the top. 2, 3, oops. Oh, these lines are off. 6, 7, 8, 9, 10, 11, 12, 15, 16. Okay, good. Okay, who needs more time to do 2 vertical 16 centimeter lines? Anybody need more time? You do. Okay, go ahead. Now, don't be an OCD about this, okay? Do it quickly and don't measure it out to the nearest a gazillionth of a millimeter and stuff like that. Right? I'm waiting for a couple people to finish their little 16 centimeter lines. See, my wife, she likes to do everything perfectly, so this would take a long time. All right, we ready? All right, now let's put a little apple here on the top of each one. Here's a little apple. And apples are about half of a kilogram, which is just about 1 Newton of weight. All right, and we're going to drop this thing down. Well, let's scale this so we can talk about real things. We'd like to know if 1 centimeter, this is our scale, equals 5 meters. That's our scale. And if we let gravity, let's make it easy on ourselves. We're going to call it 10 instead of 9.8, so we can use our head. And this is down, which is a minus direction usually, but I'll just say down. We'd like to know, how long does it take to get to the bottom of this hill? Well, how high is the hill? This thing. Well, if 1 centimeter is 5, that means 5 times, this is really 80 meters down at the bottom of the hill. That's 80 meters down there, right? So now you know how big our building is. I'd like to know, how long does it take to get down there? Okay, so we're going to do this in a graphical style. We're going to kind of show our motion. So we're going to use the formula. Let's see, speed equals gravity times time, because the starting speed was 0 in the y direction. Okay, that's in the y direction now. Nothing's going on horizontally, so we're only talking about vertical stuff, right? And how far down it is, we'll call that y, is 1/2 at squared, but we're talking about gravity. And it has no starting speed. So this is where it's at, and that's how fast it's going up there. So these are your 2 primary equations to use when you're dropping something. We did this in chapter 2, and you took a test on it, so this is very familiar to you, okay? So all we have to do is substitute in t for time, and we can find out where it is. So let's do that, and then we have to convert because it's scaled. So So this is 5t squared. And we're scaling it by a factor of 5. So 1 squared times 5 tells me that I am 5 meters down, which is 1 centimeter. I'm going to put 5 meters there in the first second. Everybody get it? So we're 5 meters down, which is actually 1 centimeter. Now in 2 seconds, 2 squared is 4 times 5. It's going to be 20. So that's going to be down here. Scaled, it's going to be here. 4 centimeters down is 20 meters. Now this is good for apples. It's good for little brothers. Anything that you let go of neglecting air friction, in 1 second, they're going to fall 5 meters, which is more than a story. So if something's falling 1 second, they're going to get hurt, probably, or the apple's going to smash. All right, now let's put in 3. 3 squared is 9 times 5, but we don't worry about the 5. We're going to come down a total of 9 centimeters, and that would be 45 meters down. Everybody see how to do that? And now we do the last one. Let's see. 4 squared is 16, right? No. Yeah, 4 is 16 times 5. That's a total of 16 if we scale it. So this is going to be 80 meters down. Everybody see it? 80 meters down. So it hits at 80 at 4 seconds. Now, if gravity is up here is 10 in 4 seconds, how fast is it going to be going? V final is going to be 40 meters a second down. Or I could put minus on there too. So that's where it is and how fast it's going for that left side. Okay, everybody with me? All right. And if you can't see what I'm drawing, you can listen or do something else. Okay, here we go. Now I'm going to toss it to the side. This is called a horizontal launch. So I'm going to keep my little lines so I can use them from the left. And I'm going to put 4 equally spaced lines to the right. 4 equally spaced lines to the right of the right-hand line. See if I can make them about equally spaced. So here's one. Here's another one. Here's another one. I want 4 vertical lines equally spaced from the building. 1, 2, 3, 4. Here we go. 3, 4. We used to have kids roll balls down a ramp and get this data with a carbon paper, and it would hit a board and locate where they hit. But we're going to do this just on our own. Okay. I'm going to say we see this thing moving for 4 seconds. 1, 2, 3 seconds, 4 seconds. All right, this is, now if this was 2 centimeters, that means I've launched this thing horizontally at 10 meters per second. All right, oops, let's get that up there so you can see it. So I've launched this horizontally at 10 meters per second, but no meters per second going down. So it's launched only horizontally. If I could turn off gravity, it would go from here to here in the second, here in the 3rd second, and here to the 4th second. If there was no gravity, it would be in uniform motion, just like on a car, on a railroad car, and it would just coast along, right, with no gravity. But now we have gravity acting on it, and we know from the left side over here, in the 1st second, how far down does it fall in the 1st second from where it should be? It falls 5 meters, and if we draw that line over, we find out that that's here, 1 centimeter down. We've already done that calculation. So let me say it again. In the 1st second of free fall, all objects fall out of where they would be by 5 meters. Let's do the next one. Here we go. You guys can do this with me. In the first 2 seconds, totally, now it's going to be down 20 meters, which is 4 centimeters on our chart. Now we're going to keep going. in the first 3 seconds. Now it's going to be 45 meters down. So the same vertical motion is happening whether it's dropped or launched horizontally. And then over here, we can find that at 4 seconds, it hits the ground. Okay, hits the ground down there. Now, being the beautiful artist that you are, we're going to draw that curve. And that's the path it would take if we had a nice strobe camera, a strobe light and a camera, time-lapse camera, we would see it follow that path. All right, it would follow that path. It's beautiful. Why? What shape is it? What kind of a shape is this? Well, we mentioned before, it's a parabola. Parabola. Why? Why is it a parabola? We have something in one direction that's changing by a squared amount on the other axis. So one axis is linear, progressing easily. The other one's a square term. So y equals kx squared is the formula for a parabola. And that's our drop distance right there. Okay, so it is a parabola. Okay, isn't that beautiful? This is beautiful. Okay, so where is this at over here from where it started? If we call this x equal to 0, this x would be 40 meters over. All right, so that's the x location. Sorry, that's the x location. Where is it vertically? Well, if this is x, if y equals 0 up here, then y is going to be equal to minus 80 meters. That's also its location. At the end of 4 seconds, that's where it's at down there. Sorry, there you go. Everybody got it? Now, if you have a question about what we just did, you have to ask it now because I'm going to turn the page over in a second. Anybody have a question? Yeah. I know there are workbooks where I could hand these sheets out to you and you just kind of go through all the motions, but I think it's okay for you to try to draw them out yourself. All righty? All right.
Wait, Mr. O'Leary?
Yes.
Yeah, but sorry, because of the internet, I couldn't ask in time. Like, why is it 40 meters again?
Oh, up here, I launched it up here 10 meters a second for 4 seconds.
Oh,
Yeah,
okay.
so it went 10, 20, 30, 40, right?
Yeah.
And then it had 4 seconds to go over and 4 seconds to fall. So horizontally it went 40, but vertically it fell down 80.
So the horizontal velocity didn't change?
Right, unless it runs into birds, leaves, water, trees. Okay. There's nothing to affect the horizontal motion. Okay. Until it runs into something. Okay. Ready? One more big drawing. I'm turning my paper over. I want you to do the 16 centimeter thing again real quick. And this is going to take up the whole page, so feel free to be liberal with your spacing. All right, so I got my building and I've got my ground level. Okay, here's 0. Okay. Everybody got their 16 mark? Please do that. You can label them if you want. We're still using the scale 1 centimeter equals 5 meters. Gravity is still 10 meters per second squared down. Vy is 0. Okay. No, that's not true. We're gonna launch it at an angle.
Mr. O'Leary, could you move your paper a little to the right? Thanks.
There we go. There we go. Okay. Who needs 30 more seconds to get their 16 centimeter line done? A couple more people? Okay, go ahead. I don't want the big Russian. Let me know if you're finished. That's a joke. You know, Russian and Finnish. Okay. Okay. All right, ready? We're now, instead of dropping it or throwing it out horizontally, we're going to throw it down at an angle. So I want you to pick any angle you want. I'm going to keep my same scale. And go, just make an angle to not horizontal, below horizontal. And I'm going to go every 2 centimeters and make a mark, as if I threw it at 10 meters per second again when I launched it. So this is just tilted from the one we just did. Once you see this has everything to do with your homework that's due on Sunday night, okay? Trajectories at angles. It's interesting. Okay, you ready? So I'm going to launch this thing. This is the launch speed of 10 meters per second. So we're going to call that V equals 10 meters per second equals the launch speed. That's how fast it comes out of your hand, out of the gun, out of the bow, whatever it is. How fast does it leave? And it doesn't have a direction to it. That's a speed. It's not a velocity. Okay. If we could turn off gravity, I want you to make a mark. If we could turn off gravity, here's where it would be in the next 4 seconds. 1, 2, 3, 4. Just like we did on the page before. Now I want you to draw some vertical lines at each of those 4 dots. Just some vertical lines. Because we got to find out where it drops to during those seconds. What does gravity do while it's moving over? Gravity's pulling it down somewhere. Okay. All right, everybody set? Who needs 30 more seconds? Wave your hand. Okay. Thank you all for being such good physics students. I appreciate it. Another minute here. Hold. Now we've got 4 dots, as if gravity could be turned off. If I threw it at that angle, it would keep that angle and keep that spacing the whole time, all right? But I said I threw this at 10, and in 1 second, here's the trick. Please look up, even if you're not quite ready. Look up now. In 1 second, we saw from both of these things over here, how far does any object fall out of where it should be in the first second? Falls 5 meters, which is 1 centimeter. Now, please be careful. I'm going to look here and come down. I'm going to use my ruler and come down 1 centimeter below that 1 second mark. And that's where it really goes in that second. 1 centimeter below where it would go if there was no gravity. Now that's 1 centimeter. That's 5 meters actually of dropped out of position. We did that on the other side twice, so this should be familiar. So how far will it drop in the first 2 seconds? 20 meters, right? We come back over here, we go, 20 meters here and here. How many centimeters is that? That's 4 centimeters below this point. So I come over here and get 1, 2, 3, 4. I'm going to use my fingers, or you can use a ruler. 4 centimeters below that point is 20 meters below where it would have been. Okay, this is 4 centimeters. 1, 2, 3, 4. Okay, be careful there. It's 4 centimeters below where it would have been. Then we have at 3 seconds, let's see, that ended up being what, 9? So I need 9 centimeter drop. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to use my fingers here as calipers. Let's say 9 is about in there. That's 45 meters down. Okay, I'm going to zoom out just a little bit. Okay. Uh-oh, I'm running into the ground down here. Something's going to happen. But what if there was no ground? Where would it be at the 4th second? It would be how many centimeters down? 16. So I'm going to use my hand and say 16 lower than the 4 centimeter mark is down in the ground down here. That would be a total of 80 meters drop from where it would have been. Okay. All right, everybody see it? Now draw that curve and let's find out, when does it hit the ground? When does it hit the ground graphically? This again is a parabola. If you did it nicely, it'll be beautiful. Okay. Now this is 3 seconds. It's still in the air. This is 4 seconds. It never gets there. So when it hits, T hit is going to be about between 3 and 4 seconds, someplace around 3.5 seconds. That's when it's going to hit the ground. It never gets to that 4 second place. Okay, this is the ground down here. And I think we're okay. Now we're still using the scale of 1 centimeter to 5 meters. Any questions on this? We need 30 more seconds to finish their little drawing. Anybody need 30 more seconds? I'm looking. Now you guys down on the bottom down there, if you can turn on your cameras, that would help me keep track of who's doing what. If there's an internet problem, you can leave it off, but that's all right. Okay. All righty. So let's go on. Enough of that. All right. So let's talk about some vectors, I think, next. Oh, I got it. Okay. I have one little question I want to ask you about this. Let's get rid of this over here. Okay. I want you to draw this with me, okay? And I'm going to use a new piece of paper. There's a new piece of paper. I used too much room on that one. There we go. Enough of that. Let's say you're a policeman, a police person, a good policeman, okay? Police woman, police, what do they got? Just police? What's the neutral term? Police person?
Officer, police officer.
Police officer, yeah, good, thanks. I have to watch my inclusion terms, okay? A police officer, thank you. Some of them are assigned to accidents and they go out and they measure stuff, and I don't know. Have any of you been in an accident in the last year, not caused by you, but been involved in some way in an accident where the police came? Anybody in a car? None of you? You have. Can you tell us what happened?
I mean, I was just like driving and someone pulled right in front of me and there's an accident. Yeah.
So you hit them?
Yeah.
Was it
But I was not at fault.
Was it your fault?
No, it wasn't.
Oh, you're lucky, because sometimes they say if you hit somebody, then it's your fault, no matter what, sometimes.
No, I mean, they made like an illegal turn.
Okay. Yeah. Well, shame on them. Okay, here we go. So police officers come and they know physics, just like you know physics. So please draw this. There's a bridge that goes over a stream. And we see when we come across the accident, the police sees that the police officer sees that the car has gone through the bridge and is buried into the muck over on the right side.
Mr. O'Leary, can you
Can you
like try?
move it a little bit? It's a bit bright on our end.
Yeah.
There we go. Now you can see it. Okay.
Yeah.
So it's going to go na 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 na, and it goes down, and the car gets stuck on the right side. And we see that the railing has been peeled away because of this accident. There's some railing that was there, and the policeman makes two measurements. The police officer. We find out that the drop distance is 4.9 meters. And that the distance from here to here is 24 meters. Okay? 24 meters from right below where it's open to where the car is stuck in the muck. Okay. Now, the policeman wants to determine, would they think that this car was speeding or not? Speeding? Question mark. Well, the speed limit was 55 miles an hour. mph, which is 24 meters per second. Okay, everybody see it? So we need to determine, at least, is it automatically a speeding ticket or not? Or what else do we need to know? Okay, so that's the question. And what's your reasoning? Probably speeding. It takes to crash through anything, you're going to lose speed. Okay? You're going to lose speed when you crash. That's conservation of energy law. And to crash through, we're going to say that these railings that were up here probably were made of something that was going to resist them falling off the bridge. They don't want people driving off the bridges, right? So they're probably made of aluminum, steel, or pretty thick wood beams, some wood. Okay, so probably they don't want you driving off into the river. Okay, they'd rather have you get your car smeared and stay on top. Okay, what else would the police do at an accident to determine speed? They're going to look also to see if you have some skid marks. Skid marks. Skid marks means that you did panic braking and you slid into the railing and left a whole bunch of tire, rubber marks on the road. And the more you skidded, probably the faster you were going. Well, they can figure stuff out. So they're going to measure these skid marks. They're going to measure how long they are. They're also going to measure the road. Was it dry? Was it wet? Was it gravel? Was it, what kind of road conditions are there? And also they're going to check your tires and see if you have baldies or not, because baldies tend not to stop very well, especially if it's slippery outside. So they know enough friction, physics to figure out all this stuff, and they can determine your starting speed when you started that skid. Okay, so probably this person was, there's a railing. Sorry, I didn't show you that. This railing got peeled away when they went through the side of the bridge. Okay, I got it? Okay, so anyway, there's a lot of physics there if you want to become a police officer in charge of traffic investigation. There's a lot of physics here. Okay, let's move on. The beginning of the chapter also talks about, remember we talked about these things called scalars? And I'm going to get into vectors here in a second too. A scalar is something where you just know how much of it you have. Quantity only. 5 meters, 5 kilograms, 5 kilometers, all right? So those kind of things is quantity only. But we want more information than that, so we're going to go for vectors now. And I know that most of you have studied vectors in pre-calc or calc AB or back, I don't know, does trig, what's the course before pre-calc here? What course did you take? Geometry?
Algebra 2.
Algebra 2? Did you do vectors in that? Well, at least geometry you did triangles, and that's the main thing we're going to be doing. Okay, here we go. So vectors, we're going to only deal with 3 of them today, all right? But everyone has quantity, which is the same as a scalar. And it has a direction, which gives us a whole lot more information than just knowing how much there is, all right? How much there is. Now, we're going to only deal with 3 of them. We're going to do displacement. I'm going to use an X for that with you, because that's what your book uses. X equals horizontal displacement. And I put the little arrow above it, meaning we know what direction to go. So if I asked you to move 3 meters east, I know, if I know where you started, I know where you ended up, okay? If I said just move 3 meters, you could have done almost an infinite number of things. Let's use Y for the vertical displacement, like 3 meters north or 3 meters up. Those would be a special movement, right? Let's use velocity, such as 50 kilometers per hour north. I know which way you're heading, right? Let's use acceleration, and we'll talk about gravity today. So that's negative 9.80 meters per second squared. And that minus means down. Whether you're going up or down, gravity is always going down. So gravity adds a minus 9.8 or minus 10 if you round it off to your velocity every second, vertical velocity every second, okay? So let's do some adding of vectors. And this is very useful, okay? And I'll talk about why in just a second. The first is graphical. Graphical, adding vectors. All right, adding vectors. Now I'm going to give you 4 quick examples, and I'm going to use terminology like your book uses, okay? So you get used to it. I'm going to tell you the components. So let's say this is X and this is Y, and I'm going to add them together. They're both, I put the tail of one onto the tail of the other, and we're going to make a parallelogram. All right, we're going to make a parallelogram, a box. So we're going to draw this box. And from where they start, I make an arrow going out to where the far corner is. That's a diagonal. And we're going to call that the resultant. Resultant. Okay. And this, so the resultant R equals X vector plus Y vector. And those are called components. X and Y components. Components. Okay. X and Y components. R is the diagonal called the resultant. A resultant means if you add everything up, what would be the result? Okay. The displacement result, the velocity result, the acceleration result, all those force results, all those kind of things. What if you could replace all the little bits with one thing, that would be the result. Okay, so let's do 3 more real quick ones. Let me give you one that's going this way, and let's give you another one that's going that way, and let's give you another one that's going down here. Okay, let me give you 3 little quickies. Right, so you go ahead and draw in the resultant. I want you to label with arrows the X, Y, and R vectors using the parallelogram method. This is easy. I'm sure you've done it before. If you have any questions, I'm going to go over right with you. Okay? All right, I'll start right now. I'm going to label this X. I'll label that Y. Make my parallelogram. Draw my resultant. And I'm done. Okay? I'm going to do the same over here. Make my parallelogram. Label this X. That's in the negative X direction, but it's still an X. This is a Y. Now my resultant goes over there. Okay? This one, I'm going to make a box, come down over here, and now that's my result. Okay? So I'm finding the resultant as the diagonal of a parallelogram. Okay? Doesn't have to be a box. Any parallelogram would work, even if they're all at angles. They don't have to all be at right angles. I made those easy. Okay? Now, what if you're given the components? You can find the resultant. All right, here we go. If you're given the components, oh, no, given the resultant, sorry, that's the resultant, find the components. Components, okay? Find the components given the resultant. So let's do a few of those. So let's say I have a resultant that's here, and I have another resultant that is here.
Could you move the paper?
Yeah, sorry. There it is, okay. So I'm just kind of randomly placing some resultants on here. And let's do one that's down over here someplace. So if I said, for those 4 examples, draw and label the components, the X and Y components. Now, this is graphical method. You're not using your calculator right now. So if we had scale drawings, like 1 centimeter equals 1 meter or something like that, we could actually get some useful results here. So here we go. Now, draw a parallel, a box, actually. I don't want it to be a parallelogram. It's got to be the box. Now label the X and Y components of it. Okay, so you make a box with that resultant as the diagonal. Let's do that again. Make a box. Nice and squared off. This isn't any old parallelogram. It's a box. Now this is X to the left, and this is Y going up. Okay. Go ahead and do your own if you want. Make a box. X to the left, Y comes down, and one more. Here's X to the right. Here's Y coming down. Have I got it? So this is called graphical methods. Graphical methods. No calculator yet. No calculator. Everybody got it? All right. Let's go now and do a toss-up. Okay, this isn't Wheel of Fortune or anything, but this is a toss-up. So I want you to make a beautiful parabola. I'm going to use the back of my paper. We need a lot of room for this. And now, instead of launching it horizontally or dropping it, I'm going to throw it into the air at an angle. This is my apple. This is my friend down here that's going to throw it.
Can you move the paper a little bit?
Yep. Sorry. And this is kind of a SpongeBob SquarePants person. And they're going to toss this apple up into the air. Let me back this off just a little bit so you can see what I'm trying to do. I'm making a big old mama parabola. Okay, I think you can kind of see it. Sorry, there's a little glare off the paper, but that's okay. All right. Now, I'm going to say that this thing gets to the top in 3 seconds. So in 1 second, it's here. And 2 seconds, it's here. 3 seconds, it's at the top. Okay? Takes 3 seconds to get to the top of this thing. All right. And now by symmetry, we know that it's going to come back down over here. This is 4 seconds by symmetry. Over here, and even is 5 seconds. And over here, and even is 6 seconds. So it's back down to where it started. Okay, beautiful parabola. Now the physics of this say, and you're going to start putting on some layers on this thing. I'm going to toss this thing at 5 meters per second sideways equals Vx. Okay? But we know that horizontal motion does not affect vertical motion at all, and it keeps it until it runs into something. So while it's in the air, this is going to stay the same. So go ahead and put that on all of them. These are the velocity vectors now of 5 all the way, all the time. Until it hits. So horizontal motion does not affect vertical motion. Now, vertically, we know that gravity changes things. But let's say it started at, we're going to use gravity up here as 10, so that we can do stuff in our head, down. Okay? We're going to start by throwing this thing up. I don't know if I can scale it very well. At 30 meters per second is the starting vertical speed, 30 meters per second. That means it was launched at an angle, right? Not vertically, not horizontally, at an angle. Well, at the instant it's launched, we'd like to find out what was that muzzle velocity, what was the launch speed. So let's draw our little triangle. Draw this diagonal. And I'm going to call that V. And yeah, I'd like to know its speed and direction. So let's put a vector sign on that. What is V? In meters per second. And what's the angle? Okay. Now we should be able to do that from what we've just learned. We should be able to get V. Let's use Pythagorean theorem. A squared plus B squared equals C squared. Okay. C is the resultant, so that's V. And we're talking about x squared and y squared. Okay. So V is the square root of 30 squared plus 5 squared. And we can get how fast this thing was launched at. That's the launching speed, the muzzle velocity if it's a gun, or the launching speed if it's a bow and arrow, or a pitcher, or volleyball server, or whatever. Okay, what's the launch speed? And let's see what you get for this. Type it in over on the right if you're done already. How fast does this thing launch? And it has components of 5 and 30. Yep, 30.4, very good. So 30.4, slide that up so you can see it. Zoom it in just a little bit so you can see. There we go. Yeah, so it's about 30.4 meters per second. And what's the angle? Well, we've got a triangle now. It's 5 over and 30 up. And we want to know that angle. What's that angle, launch angle? Is anybody here on the robotics team this year? Anybody wave your hand if you're robotics? I have 2 people already. Well, they have to launch some stuff into a target. So they're really excited about this month in physics because they're going to learn how to do all that. Okay. So what's that angle? 5 over and 30 up. Give me an angle here. Ah, yes, 80.5. I'm going to round that off to 81 degrees. Now, if you don't know how to do that, it's the angle whose tangent is opposite over hypotenuse. So that's the angle whose tangent is 30. I'm sorry, over adjacent, sorry. 30 over 5. Now you got to make sure your calculator's in the degree mode, not the radians mode, to do these things. I got it? Okay. Who needs 30 seconds to catch up? All right, I'm going to keep moving. What have I got? Half an hour? Okay, here we go. So now let's go and put on these vertical things. Well, if gravity's 10, adding a negative 10 every second, this is going to go from 30 to 20. That's what gravity does. It adds a negative 10 every time. And now this one's going to be a negative 10. We add a negative 10, that makes this one a 10. Now it's stopped going up. It's at the top. It stopped going up. And by symmetry, in 1 more seconds, we know that it's going to be going down at 10. The arrow going down means down 10. And then 20 over here. 20. And then 30 over here. Okay. Pretty easy, huh? I'd like you to calculate what is V4, 5, and 6. So what's this one? This is V4. What is V5? And what is V6? Now I'm talking about speeds. Now V4, V5, and V6. Okay, I'm talking about speeds now. Let me zoom out so you can see what I'm trying to do here. There we go. V4, 5, and 6. Let's do 6 first. We already know it. Wow. 5 over and 30 down. That triangle means, oh, what is it? 30.4. We know that one already. We already did that one. We already did that one. Now let's do V4. Up here, let's see. 4. It's 5 over and 10 down. And then down here we have V5, we have 5 over and 20 down. All right. As soon as you get V4 and V5, put them down there for me and I'll give you a virtual pat on the back when you're done. What's V4 and V5? Go ahead and type them in. If you don't know what you're doing, we're taking the triangle. 5 is the horizontal and 10 is the vertical for 4. 10 squared plus 5 squared equals, and then take the square root of that, and we get the diagonal. Okay, I've got 20.62. Yep, that's right, for the 5. 20.6. And let's find a V4 up here. 11.2, that's right. So those are the two numbers I was looking for. V4 is, it's 10 down, 5 over, so it's a little more than 10, so that's reasonable, 11.2. At the 5th second, we have 20 down, 5 over, so it's a little more than 20, so 20.6 makes sense. Okay. Any questions on this problem? So this sets you up for success for Sunday night's homework. Sunday night's homework. Okay. Now I have 2 things left for you. 2 things left. Let's. I found. Okay, let me put this over here. I found for you. Let me go back to me. Okay, me, FaceTime. Okay, I'm going to show you a short video clip produced by the AP computer people, AP College Board people. And at the end, I'm going to get your critique of it. Now, this lady is going to try to teach you in just a few minutes what I've been spending an hour on. And I want you just to realize that this is a resource for you. So I'm going to show you where they are if you've never done any on College Board. And then I'm going to let you listen for her little speech. And it'll be a summary of what I've been trying to teach you all day. Now, this is a lady that's a physics teacher. She's a master teacher hired by College Board to give you this lesson. And she does many lessons. And you'll see where they are. So I'm going to talk for a little bit and get her started. So I'm going to do a share screen. So please don't go fading off because I want you to watch this. I'm not going to do this very often. This is just an example of what you could see from College Board. So I'm choosing to show you this right now. So stay with me. I'm going to do a share screen, share my main screen. I'm going to come over here and find my AP Physics stuff. Okay, here we go. Here's AP Physics. I'm going to go to the Zoom, not Zoom, sorry, I didn't want that. Get out of there. How do I go back? I didn't want that, sorry. I don't want to launch a new meeting. Okay, let's do this guy again. Okay, so down here, video dropped versus, now I gave this to you in your week 5 planner, okay? And this is the one right here. I'm going to click on that. They're probably going to make me sign in to AP Classroom. I doubt if they've left me on. I've been there before today a few times. Come on. Come on. Hang in there. Oh, it's not loading. Okay, I see it up here. All right, whistle for 30 seconds. Maybe it'll load up. Oh my goodness. Boy, is that taking a while. All right, we're going to back out and do it again. Oh, here it comes. Here it is. Please sign in. Welcome back. Yay. Okay. Now, when you go into WebAssign or into AP, this is where it is. And this is a video that you can get back in the classroom. This is video 1.1, video 8, down here, daily video. There's 15 of these. We will compare the time of in air of an object dropped and launched horizontally, and it's about 9 minutes. So, and this is the lady speaking in the corner. Give her your respect, all right? Some of you girls out there may become physics teachers, so I think she's great. I love physics teachers. So here we go. You ready? 9 minutes. Just hang in there. Don't get bored, and see what she says compared to what I say. And they're very similar. Okay, here we go.
Hi again, everybody. This is Mrs. GB, and today we're going to compare free fall, which we've been talking about, to an object that's going to be horizontally launched. So we want to compare that time in air of an object that is dropped and horizontally launched from the same height. So what are we going to do? We're going to compare the motion of a ball that is dropped to the motion of a ball that is horizontally launched. We're now going to also look at not only how do we describe motion in one dimension or horizontally, we're also going to look at what is it like if there's two-dimensional motion, so both horizontal and vertical motion at the same time. And if we drop the ball and horizontally project a ball from the same height, which one will hit the ground first? So if we look at an example here, I've set up a device that can both drop and launch a big marble at the same time. And so I'm going to show the video here, and then we're going to look at it a little bit closer. So one more time. All right, so let's look at what's going on here. I'm going to switch over so I can draw on my screen, and we're going to look at the equations. Okay, so let's first take that ball that was on the dropped side. So it fell straight down from that device. And so the first thing I want to look at is let's kind of make what we call a motion map of this. What does that motion look like of the object if we take it in snapshots of time? So it started at rest. And then what do we say happens when an object is in free fall in the air? It's going to accelerate downwards at a rate of -10 meters per second squared. So after one little instant of time, it's going to be traveling a little bit faster downwards, and then a little bit faster downwards, and a little bit faster downwards until it strikes the ground. And as you can see, those dots are spreading out, meaning it's traveling a greater displacement in the same section of time. And then let's look at how would I calculate how long it takes for it to hit the ground if I knew the height that it started at. So if I know what the y height is, and I know that final height is 0, and I know that the acceleration, since it's again falling through the air, is g, and I want to know what the time is, I also know that it starts from rest, so I know the initial velocity is 0. Then, which of our kinematic equations is going to give us that relationship for position and time? It's that y equals y naught plus v naught t plus 1/2 gt squared. And again, if we look at this specific situation, it's starting from rest. So we can say delta y equals 1/2 gt squared. And so if we arrange that, we can say, well, the time that it's in air is equal to, well, we're going to bring the 2 over, 2 times delta y, we're going to divide by g, and we got to take the square root. So that time is equal to the square root of 2 times delta y over g. So that's the one that's just dropped. Okay, let's compare that. So that time is dependent on the height that it starts at and the gravitational acceleration. Let's now look at that ball that is horizontally projected. And this is now different because not only do we have that ball still falling towards the center of the earth and accelerating towards the center of the earth, but it's also traveling horizontally as it falls. So if I kind of just draw out the motion, it was doing this until it struck the ground. So we kind of, when we're drawing a motion map of this, want to kind of think about those separately. And the same thing when we calculate. For an object that's traveling in 2 dimensions, that has horizontal and vertical motion, we have to take those separately. We have to parse it out and look at first what's happening horizontally and what's happening vertically. We got to look at them separate. So we kind of already have been talking about what's going on vertically. So let's do that first. So if we look at this motion map, well, its initial y velocity is 0 because it's being projected horizontally. That means straight out in that x direction. So it has no y velocity. All of its velocity is in the x direction. And so our initial y velocity is 0, but we do have initial x velocity. If we take one little instant of time later, well, it's still accelerating towards the ground. There is still only that gravitational force acting on it. And so the acceleration in the y direction is still -10 meters per second squared. So it's going to be going a little bit faster in that y direction, and then a little bit faster in that y direction, a little bit faster, right, until it strikes the ground, speeding up in that y direction. And if we look at the x motion, well, do we have any factors that would cause that ball to speed up or slow down in that x direction? The only interaction that we have is that gravitational force between the ball and the earth. And so there is no interaction in the x direction, which means there will be no change in motion in the x direction. So whatever velocity in the x direction we start with is going to be the same. There is no acceleration in that x direction of a projectile because there's no forces or no interactions going on. So all the time, it has that same x velocity. And we can kind of use a table sometimes to help us organize what's going on. Because again, we always want to keep that horizontal motion separate from the vertical motion. And so if we look here at the horizontal motion, well, what we can look at is that starting position we can call 0, right? Wherever it lands is that final position x. Our initial position we're going to call 0. And we know that our acceleration is always 0 in that horizontal direction. There is never going to be acceleration in the x direction for projectile motion. And so I can use an equation. If I look at that second equation here, this is our most common equation we use for projectile motion. We can use the other ones depending on what we're looking for, but this is usually the one we look at the most. So if I apply this in that x direction, well, there is no acceleration in the x direction, so the 1/2 at squared goes away, and we're left with, and our initial x is 0, what we're left with is an equation that we can use that x is equal to v naught t. And that's always going to be true. There's never acceleration, and so if our initial position is 0, we can always use the x as v naught t. And that v, I'm going to say, is always constant. In that x direction, the velocity is always constant. If we apply this now to the vertical motion, well, it's just like free fall in the vertical motion. So our acceleration is still g. Here, if it's horizontally launched, we have 0 y velocity. And so if we look at our same equation, that second equation, let's apply this now to the vertical direction. Our a is going to be equal to g, but we have no initial velocity. And so we can say again that delta y is equal to 1/2 gt squared. And our time is always going to be that common link between the two. So if you can find the time in the y direction, if you know the height, then you can plug that into the x direction and find the range, or vice versa. That's kind of our common link to go between that horizontal and vertical motion, is that time, because time's always the same in the horizontal and vertical. So let's compare now these two situations and see which one of these is going to strike the ground first. In the one that is dropped, we said that time was equal to the square root of 2 times delta y over g. And let's look at here. Let's apply this same equation now at our vertical motion. What would we get for time? Time here is still going to be 2 times delta y over g square root. And so no matter what, no matter how fast that ball shoots off that apparatus, it's still going to hit the ground at the same time if it starts at the same height as the dropped. And you saw that in the video. And we're going to go back, we're going to see it one more time. Okay, so let's look at one more time and let's see it. Well, look at that. They hit at the exact same time. You can even go back and see in slow motion hit. And you can hear it strike at the same time too. So, okay, so what are our key takeaways today? Well, our horizontal and our vertical motion are completely independent of each other. You can't combine the two. You have to think about what is going on with your object in the vertical direction, what is going on in the horizontal direction. Our main things to remember are that in that horizontal direction, that the velocity is always constant. The acceleration is always 0. And in the y direction, that vertical motion, it's just like free fall. So our acceleration is always g, or negative 10 meters per second squared. Okay? And we can use that time as a common link to go back and forth between that horizontal and vertical motion. So thanks for joining me, and I'll see you again soon.
All right. So I don't know what you thought about her presentation. I think she speaks well. She was very succinct, and she was trying to teach the same thing I was, but in a different way. So there are about 15 of these on Unit 1 on College Board in my classroom waiting for you if you want to go through them. I'm trying to give you the essence of all of them myself. Okay? I have just 3 quick little practice problems to set you up for success for the homework. And if you have anything that you'd like to say over on the right, you can. But I'm going to go ahead and switch to Elmo again. I'm going to give you 3 practice problems, and then I'm going to turn you loose. So let's see how quick we can do them. You ready? These are Chapter 3, homework practice. And a lot of people say, please help practice these with us. Okay, the first one says, I'm going to go 5 kilometers east. And then
Right, Mr. O'Leary.
Oh, yeah, sorry, bright, too bright?
Yep.
Yeah, that happens. I got to figure out how to make it less bright. I guess there's probably a dimmer thing on this somewhere. No, that's just a zoom. Okay, I'm going to go to 5 kilometers right. I'm going to go 3 kilometers north. And I'd like to know, how far away am I? And we'll call that R. And what's that angle there? How far away as the crow flies, they used to always say, or nowadays they say, as the helicopter flies. Okay, how far away am I from where I started, and what's that angle? Okay, we'll talk about that. Go quickly. Let's see how you do. 5 over and 3 up. Again, we're using tangent. If you want help with tangent, you got to say something one way or another, and I'll help you. You people that are, if you can, show me your video next time. I don't mind the top of your head. All right, you're not bald like half of my friends. Then I can tell you. Please type it in over on the right, and I'll give you a thumbs up or a virtual pat on the back if you get them right. Well, somebody's typing over here. 5.83 and 31 degrees. I'll agree with you. So 5.8. I'm going to go one more digit than the data. The data was in 1 digit of information. I'm going to go one more digit than that, 5.8. And then the angle is about 31 degrees. Now, I want you to make a note that angles, absolute angles, start on the right and go counterclockwise. They're measured that way. So I can either say, now, what would be another way of measuring that 31 degrees? I could say 31 degrees north of east. Okay, that's another way I could say it. And that would also tell me exactly what direction we're talking about. Okay, that's sample 1. Sample 2, I'm flying an airplane at 100 kilometers per hour. It's a slow airplane. Okay, 100 kilometers per hour. But there's a side wind coming in from the west. This is north. Coming in from the west, it's blowing me towards the east at 10 kilometers per hour. I'd like to know what's my velocity vector and what angle is this over here. Okay, let's do that one first. That's theta. Okay. Should only take you a couple minutes. As soon as you're ready, give me a little type over on the right. Now, if you're struggling with this, you can get help or just write down the answers when we're done and look in your book, or you can ask me for help too. If anybody's missing a lab or old homeworks, you can still ask for extensions. I want everybody to get a good grade and know what's going on in here. Oh, here come some numbers. 100.5 for the speed, 100.5 kilometers per hour. Yeah, if we assume those are perfect, rounded 100.5, 101 would be okay too. And then for degrees, I've got the little guy is 5.7 degrees. So the absolute angle could, so this is going to be called east of north, okay? Or we could have the absolute angle and say 80, what would that be, 84.3 degrees, which means north of east, okay? There's 2 ways to say that. All righty. Now, the last thing I want to give you is what happens when you have a whole bunch of things happening. What happens when you have a whole bunch of things happening? Let's go 5 east and 6 east. Let's go 2 north and let's go 6 east and let's go 7 south. And I'd like to know, this is head to tail method, if you were doing it graphically, what is going to be my displacement and what is this angle, okay? Now it looks kind of chunky, doesn't it? But basically you take everything that's horizontal and sum them and find what's left over. So I'm going to make one triangle. So it's 5 east and 6 east. That's 11 east. Okay, that's easy. Now I've got a 5 up, I'm sorry, a 2 up and a 7 down. So actually my resultant is 5 down. Now I can do one triangle and get the displacement vector and the angle involved. All right, go. All right, I think you can kind of see that. Zoom out slightly. Oh, there we go. So I've got a triangle with an 11 and a 5. That's a Pythagorean theorem. And I get D. Somebody give me a D. Give me a D. I got, somebody has 12. Anybody else agree? 12, 12.1, good. So let's say 12. Let's leave it at 2 digits because we're only getting 1 or 2 in the data. And what do we have for that? Theta. What's a theta? And then we'll convert that to correct word directions. And we're almost done. Almost done. Need an angle. Give me a theta. Sounds like it's a sorority call or something. Just give me a theta. 24 degrees south of east. That sounds good. South of east. And that would be legitimate. You could say that. Okay. All right. Please write down the 2 answers for that last one or any other one here. You can ask for them. But your homework that's due Wednesday night, which is 2 nights from now, is easy. It's going to take you 30 minutes. The one that's due Sunday night on what we're doing next class, which is launching at angles from heights to heights, that's more complicated and you have to use the quadratic. So the homework for Sunday night is going to take you more than an hour. So if you want to get started on that at some point before Sunday, please do that. And next class will be super important for you to understand how to do it, okay? Well, it's nice to see you all. I'm going to put this back on, get rid of Elmo and back to me over here. And I hope you appreciate, we are halfway through chapter 3 right now in one day. So we're going to do the other half on Thursday. And thank you for being in physics. If you want to stick around, please do. You can ask questions. Otherwise, sayonara, hasta lasagna.
I'm that old, but you get on. Gravitational, root 2GM over R. It's inescapable, cause I can find velocity. Miss Mills, she taught me. Gonna get 5 on this exam, but that's a guarantee. Elastic collisions I've been observing, but your momentum don't need conserving. My love for friction is concerning when you
Talk physics to me.